This is the third of a series of revision videos reintroducing you to ideas about rates of reaction. In the first two videos, you've reminded yourself of the meaning of rate equations and how to deduce rate equations from experimental data. In this video, we'll look in a bit more detail at the rate equations and in particular how to do some mathematical calculations using the rate equation, which will involve some rearrangement and substitution of numbers into the equation. Okay, so what is a rate equation? Well, as we know from the earlier videos, it's an equation that shows how the rate of a reaction depends on the concentration of reactants. So, an example of a rate equation, something like this, a very simple rate equation showing that rate is proportional to the concentration of hydrogen peroxide. More complex rate equation would look, here we've got several concentration terms in the rate equation, and we can see that there are a variety of orders included in the rate equation: second order, first order, and first order. Just be absolutely clear that a rate equation is different to a mathematical equation that you would use to calculate the rate of a reaction from experimental data. Just look at the kind of thing you would use to do that. That would be simply using the definition of rate of reaction, the change in concentration over the change in time. That would enable you to calculate the rate of reaction. The rate equation then shows how that rate is determined by changes in various reactant concentrations. So, having deduced a rate equation, what might you be asked to do with it? Well, you could be asked to calculate K, the rate constant. How will we do this? Well, we might be given some data. For example, here's data showing how the rate of a chemical reaction depends on the concentration of two reagents here, nitrogen oxide and ozone. Notice, by the way, in the table showing you the data, the appearance of these powers of 10. This can cause some confusion. You need to be aware of the fact that the number 8.0 here for the concentration of nitrogen oxide really means 8.0 times 10 to the minus 9. Similarly, the rate here is 28.8 times 10 to the minus 6. Very easy to forget those numbers when you are putting numbers into the rearranged equation for K, which we will do in a second. So, you might be told, for example, that the rate of this reaction depends on nitrogen oxide and ozone concentration according to this rate equation. So pause the video for a second and see if you can now rearrange this rate equation to find a value for K. Okay, so hopefully what you've written down looks something like this, where K will be equal to rate divided by the concentration of the nitrogen oxide and ozone. So to find K, it's simply now a question of plugging numbers in from this table of data into that expression. In theory, it shouldn't make any difference which set of numbers you use, so long as all of these are obtained at the same temperature. And I think you can be certain that in an exam question, they will ensure that all of the sets of numbers they give you will produce the same value of K. Not always true for real experimental data, however. Okay, so can you now write down the mathematical expression that you'll use using these numbers to calculate a value for K? And you can then have a go at actually calculating the actual value. Do be particularly careful of these powers of 10 here. So pause the video while you work out how to find K, and let's assume that we're using the data from the first line of this table of data here. So this is the kind of thing you'll be doing. You'll be finding the rate of reaction, remembering the power of 10, and dividing through by the corresponding concentrations that produce that rate. So we get an expression like this for K. So now let's see if you can actually get a number out for that. And what you should find is you get a number 1.8 times 10 to the power 12. Now don't worry too much about the units here. We'll explain how those come about in a second. We'll notice, by the way, that we've given the answer to two significant figures because all the data here that we're using in concentrations is also given to two sig figs. So that is the appropriate number of sig figs to use here. Notice that the value of K is really quite large, not surprising because very, very small concentrations appear to produce actually a more significantly increased rate. So K must have a particularly large value. Okay, now let's deal with these units. So If we have a simple rate equation, like say this one, how do you figure out the units of k? Well, it's a similar idea to calculation for the numerical value of k. We simply rearrange the expression for rate. So can you do that? Write an expression showing how k depends on rate and hydrogen peroxide concentration. Pause the video while you do that. What you should find is we end up with this rearranged expression here. And then if we wanted to work out a value for k, we would simply plug in some values for rate and hydrogen peroxide concentration. To work out the units, however, we simply plug in the units of rate and the units of concentration. So you might like to think about what those units would be. So plugging in the appropriate units, we end up with the units of k being the moles per dm cubed per second from the rate divided by moles per dm cubed from the concentration. That luckily turns out to be a very, very simple overall unit, because we can simply cancel out these moles per dm cubed terms on top and bottom, and we end up with simply seconds to the minus 1. So a first order rate equation like this one has very simple units for k. If you're ever asked to work out the units for k and you're struggling with it, it's always worthwhile guessing seconds to the minus 1, as that is the most common order for a rate equation. Well, what if we now have a more complex rate equation? So here's a more complex one. So can you begin by writing down the rearranged form of that, showing how k is related to rate and the concentration terms? So yes, we end up with that rearranged expression there. And now we need to think about plugging in the units of the rate and concentration terms. So if you'd like to do that, you'll end up with quite an unwieldy expression. So we have something looking a bit like this, with moles per dm cubed per second on the top, and then moles per dm cubed times moles per dm cubed, that's from the h plus squared, times moles per dm cubed times moles per dm cubed. How do we simplify that down? Well, first thing we can do is to cancel out moles per dm cubed, and so that will leave us with, if we look down here, seconds to the minus 1 left on top, but we've still got these 3 moles per dm cubed terms on the bottom. So there's 1 or 2 stages left now in the simplification. First thing to realise is that we can actually simplify this by thinking about the number of mole terms that we have on the bottom. It's moles times moles times moles. That means moles cubed. Then it's dm to the minus 3 times dm to the minus 3 times dm to the minus 3. That will make dm to the minus 9. If we're not sure about how we do that, then there's a little hint we can use later on. We're left now with seconds to the minus 1 over moles cubed dm to the minus 9. The final tweak is to get rid of that dividing sign by realising that 1 over moles cubed is moles to the minus 3. 1 over dm to the minus 9 is dm to the plus 9. So there is our final rearranged and simplified expression for the units of k. One thing always to notice whenever you've got concentration terms used in working out units, the powers that correspond to moles and dm will always be in a 1 to 3 ratio, here 3 to 9, and will have opposite signs. So if you've worked out that it's moles to the minus 3, you know automatically it's dm to the plus 9. One final method that you may be asked to use to find k is a graphical method. This can only be used if you've got a first order reaction, in which rate is proportional to the concentration of a reactant. So imagine what the graph would look like if you plotted rate against concentration of A. So sketch that out, can you? And yes, we end up with a graph looking something like this. Okay, so the rate on the vertical axis, concentration on the horizontal axis, and we have a straight line relationship. Now, have a think about that equation and see if you can figure out what we can conclude about the value of the gradient of this graph. So pause the video while you do that. Yes, the gradient of the line is actually equal to the rate constant, k. One thing that's extremely important is that this will only work and give you a valid answer for k if rate is in moles per dm cubed per second and concentration in moles per dm cubed on the horizontal axis. This will usually be the case in exam questions, but may not be the case in, for example, any experimental work that you might do. You're sometimes asked what the effect is of changing the temperature on the value of K. Well, this graph here shows you the relationship between K and temperature. As you can see, as you increase the temperature, the value of K goes up really quite significantly. We know that because the rate of reactions go up significantly as well. The reason for that is beyond the scope of the A-level course, but comes about because K actually does depend on temperature in a rather complex way. This is known as the Arrhenius equation. Some of you will be using that in your investigation analysis. The final part of this video looks at the link between mechanism of reaction and the rate equation. And a lot of this is to do with the ideas of the rate determining step. So these will be the two learning outcomes that we look at in this final 4 or 5 minutes of the video. Okay, so what do we mean by a mechanism? Well, simply put, it's just the bond breaking and bond forming processes which lead to an overall chemical reaction occurring. So you'll be familiar with organic mechanisms here, showing, in this case, bond breaking and bond forming. Here's a halogenoalkane reacting eventually with a hydroxide ion to produce an alcohol. So we've got two steps that are part of this mechanism, and they have different rates. So one of those steps is extremely rapid and one is much slower. See if you can look at the mechanism here and deduce why it is that the second step is likely to be much more rapid than the first. Well, it's to do with the fact that the second step involves attraction between some oppositely charged ions, which is going to be much more straightforward than the first step, which involves the breaking of a bond and will therefore only happen when there's collisions between molecules that possess really quite a lot of energy. So here's a way of representing the mechanism for this reaction. First step involving the break part of that carbon-bromine bond is slow, second step is fast. So the second step then, much faster than the first, which means that the first is known as the rate determining step. It's the slowest step in a mechanism, and it's the rate of that reaction that determines the overall rate of the reaction, hence the word rate determining step. So now let's look at the link between the rate determining step and rate equations. So here's the mechanism we've just been looking at, the rate determining step, and the second step, which is much, much faster. And there's a very important point to be made here about rate equations, which is that if a reactant appears after the rate determining step, it cannot affect the rate of reaction. The hydroxide ion here appears after the rate determining step. It can't affect the rate of reaction. So just pause the video while you think, therefore, what you can conclude about the order with respect to hydroxide ions. Well, the order will be 0 because they don't affect the rate of reaction, whereas any reactant that is involved in the rate determining step will have an order of 1. Having said that, there are some mechanisms in which you'll find that reactants appear more than once before or in the rate determining step, and that can have a slightly different effect, as we'll see. So, see if you can therefore use that information to suggest what the likely rate equation will be for this reaction. It will involve a halogenoalkane and hydroxide as the two possible reactants. Think about what order you'll have for each of those reactants. And the only thing that will affect the rate of reaction will be the halogenoalkane. It'll be 0th order with respect to hydroxide ions. You could include that in the rate equation with the power 0, or you could omit it as we've done here. The very hardest questions along these lines are when the rate equation, or rather when the mechanism, has a rate determining step which is not the first step in the mechanism. Here, the rate determining step is the third step in the mechanism. And here we have to use the fact that any reactants that appear before the rate determining step or in the rate determining step will affect the rate of reaction. So look at what's going on here. There's a reaction producing an intermediate that's used up, a second intermediate that's used up. So bromide ions, H+ ions, and H+ ions are introduced into the reaction before the rate determining step. They will all have an effect on the rate of reaction. And so therefore, the rate equation is going to be the one you can see here, which involves bromide ions, bromate ions, and H+ ions squared. Why? because H plus appears twice in